So here we've now cleared chapter 11, and now we're moving into chapter 12, which is how we're doing the electrophilic addition reactions with electrophiles instead of with acids and bases, with acids. One of the big differences that we're going to pick up here is that with acids, we did a relative or similar acid-base type reaction in that very first step. Okay, we just transferred a hydrogen. When we move into chapter 12, the chemistry becomes a little bit wonky. Acids and bases, or at least the acids that we're using in chapter 11, were very straightforward. They had H+, and that's where the chemistry was. We didn't have to worry about anything else. When we move into chapter 12 and ultimately chapter 24 with our electrophiles, those electrophiles can be of varying levels of reactivity, and their mechanistic detail is going to be largely driven by what that secondary piece is, what that extra nucleophile is. Okay? If that nucleophile is something that is integrally related to the electrophile, then we're going to have to change how our mechanism works to be able to address that. Okay? In my opinion, this section is very challenging to organize as far as reagents. Virtually every reagent appears to have a new mechanism, a new detail, and new pieces that you have to memorize. So what I attempted to go through and do with our electrophiles, or chapter 12, is to go through and consider the similarities or patterns within those particular reactions and try and find something that allowed you to kind of tip off on looking at the chemistry of the reagent, so that you could try and mimic and copy that even if you hadn't seen that reagent before. So we're trying to look for those certain patterns. That is exceptionally challenging because the reagents that you use look widely different across the board. Okay, so almost all of them involve some form of cyclic aspect. In some cases, it's a cyclic intermediate. In other cases, it's a cyclic transition state. In other cases, it's a cyclic product. Okay? Because we're generating these kind of cyclic things, we get a lot more selectivity behind our products, and these tend to be a lot more commonly used because we get that nice selectivity. So if we go through and look at the potential structures or reagents that we're going to encounter, I've gone through and classified them as 3-membered transitions, intermediates, 4-membered, or 5-membered. So when we're looking at the 3-membered system, it's largely in chapter 12. Bromine, it's a little bit weird here because what we're referencing with MCPBA is the reagent, but the P of that is a peroxy. So the peroxy is the oxygen-oxygen bond. We've got the carbon in diazomethane, and we've got the mercury in our mercury acetates. Okay. With the mercury acetates, I will note that I'm saying acetate even though it says X here, because there's a large variety of mercury reagents that you can end up using, and that group will change to be different things to cause different functional reactivities. So if instead of focusing on that extra piece, you focus on where the chemistry is, the mercury, that will help you qualify that. Because we're looking at reacting pi bonds to begin with, the pi bond has 2 carbons already, so if we're going to do a tri-intermediate, we're only adding 1 atom. That's why you're seeing 1 atom highlighted in each of those examples. When we move down to the tetra intermediate, you'll notice that I now have 2 atoms highlighted. Why 2 atoms? Well, if we had 2 carbons, we need 2 atoms or 2 more atoms to contribute to the 4-membered system. When we move up to chapter 24, we're going to encounter some penta systems and potentially more. And in those cases, again, you're seeing that highlightation change. It becomes a little bit more challenging because we're only using 2 out of 4 oxygens, 2 out of 4 oxygens to contribute to those. And I can't really identify that in those formulas. And then the ozone is getting you those 3 atoms. Again, we're counting the 2 carbons that were part of our alkene. So what we're trying to do is come up with ways that we can simplify how we approach these. Okay. That said, this is not simple. Okay, so let's push through to the examples, okay, or our generic system. So what we're trying to evaluate is look for those patterns. So what I'm saying is we're starting with, in all of these cases, your same basic alkene with a Lewis acid, which is going to be your electrophile, and then this leaving group, whoops, if we color code a little bit better, our electrophile, and then we have this leaving group, which is very likely to act as a nucleophile. It's not guaranteed, but it's very likely to act as a nucleophile. So how does this end up working? Well, the alkene is still going to share electrons because that's what it does, and it will share electrons with our Lewis acid. Okay? The question now becomes is what happens to that electrophilic species. So in one system, if we look at our three-membered system, our leaving group is large, okay, or ultimately really, really, really good. Okay, it is so good that it leaves the structure entirely and we don't have any problems. This would start to mimic our acid-base reactions. Okay, one of the other characteristics that's going to work out in this is that it's not just an electrophile with a good leaving group. The Lewis acid will also act as a nucleophile. Okay, it's weird to reference it like that, but that's what that second curved arrow is showing. We're saying that Lewis acid has electrons that can immediately donate back to the other carbon. Okay, remember, as those electrons come out, one of those carbons is becoming negative, the other one is becoming positive. So if that Lewis acid has electrons and has a good leaving group, what can happen is the Lewis acid will accept electrons from the alkene, it will donate electrons to the other carbon of the alkene, and then our leaving group pieces out all at the exact same instant. The end result of that is that we have this three-membered ring. Okay? That three-membered ring, depending on its stability, note there's a question mark in the next step, could be the end of it. That could be a final product. For it to be a final product, though, we would need to ensure that La in this structure was not positive. Because if it was positive, it wouldn't be stable and it would need to continue to react. If La is indeed positive, then we need some kind of secondary nucleophile to come in and react so that we could get to a final product. Okay? So if La is positive, we continue the reaction. So again, what we're trying to do is look for those pieces. What happens if, in the case of that reaction, our leaving group is horrendously bad? Okay? So in this case, if the leaving group is tiny, okay, if your leaving group is a bad leaving group, it doesn't want to leave. Okay, so it needs to be immediately stabilized. It is still acting as a leaving group because the electrons in that bond are going with the leaving group, but they are just going to immediately react with the carbon. Okay, the result is that we're moving through a transition state of 4 atoms. Okay, we aren't formally forming a 4-membered ring, but the process of making those new connections was a 4-membered transition state. Okay, and that's where we're getting that cyclic aspect. And then we would get the Lewis acid and the leaving group directly connected to our structure in one fell swoop. Okay, do we need to continue running? Well, it depends. Okay, are the leaving group and the Lewis acid, the things that we just added to our carbon structure, good to have connected to our structure? If they aren't good, then we need to continue. If they're normal or standard things to have connected to your carbon structure, then great. Leave them on and we're done. Okay, what do we define as that normal? Well, remember way back at the beginning of the semester, we simplified out our periodic table to talk about hydrogen, carbon, nitrogen, and our halogens. If we're encountering a different atom, say bromine or mercury, we need to really get rid of that different atom through some other secondary step. Okay, so either way you slice it, we're looking at an overall reaction that is an addition because we lost the pi bond. It becomes an electrophile addition because the very first thing that we do is we put an electrophile onto the pi bond. Okay? And that's going to ultimately predict our product, where the placement of the things that have happened. We would then have to move to the structure and the mechanism to understand something about the stereochemistry. Okay? Should these be wedges and dashes? Should they be both wedged? Should they be both dashed? Should one be wedged, one be dashed? Okay, which one's which? How do we decide? And the regiochemistry. Well, the regiochemistry is still going to hold based off of what we learned in Chapter 11. We're looking at where the partial negative and partial positives are of the alkene. If we can do that from our resonance, we've got the regiochemistry down. Really, the only thing we need to add into this would be what would be that stereochemical concern. Okay? Why break it up this way? If we can go through and classify things according to the three-membered transition, we can now have a conversation about what would the stereochemical concern be if we fit that category. If we fit the four-membered transition, what would the stereochemical concern be? Okay, so it can simplify some of our analysis if we decide to look at those patterns. You do not have to decide to look at those patterns. Okay? Full disclosure, you do not have to do that. What I'm telling you to do is something that I think is useful because it helps to kind of organize that thought. Okay? So we're going to now move through and take a look at some examples of the tri-intermediates and how that's going to affect our stereochemistry. And you can decide if you find that helpful or not. Okay? We'll do the same thing for the four-membered ones, and we'll throw in a couple of the extra kind of secondary issues that can pop up with these question marks. Okay? So, three-membered. Okay? There's a lot of stuff here. So let's pull it back. Let's erase some of that so we don't have to stress about this, okay, as much, and let's evaluate what we're talking about. Okay? So what we're reacting is a pi bond. Okay? That pi bond is formed by the overlap of p orbitals, which means there are electrons on either side of that pi bond. Okay? And that's why we're showing the wedge and the dash. We've taken our structure that we would normally have shown like this, and we've taken this side of the molecule and we've pulled it out at the board towards you and kind of rotated a little bit so that we're looking on it on edge. This on edge allows us to see the pi bonds or the p orbitals so that we can now have the next conversation, which is for this reaction to occur, those electrons must come out and react with our electrophile. Because this was the tri-intermediate, we know that electrophile has electrons and can immediately react back. Okay? As it does so, the leaving group will leave because now that electrophile has exceeded the amount of bonds it can have. So the electrophile gets booted from the structure, and we would end up with this looking intermediate, okay, with our leaving group, okay, very likely as a partial or formal negative charge. If it is formally negative, we're probably going to see some kind of resonance associated with it, resonance or large size, because one of our rules was that that leaving group needed to be stable on its own. Okay, so if it fits that, then great, we're following the same pattern. So now the question would be, if this structure was indeed unstable, actually we don't even need to get there to address our stereochemistry. If we looked at this product, we might say, well, there's no stereochemistry associated with it, and you would be correct. So let's revert back to the starting material and let's make sure that we can see this. Let's go ahead and throw on some stars. Because this reaction all happens simultaneously, when I look at the product, those stars must still be there, okay, in the exact same conformation. Okay, while we may now have a sigma bond because we've lost the pi bond, we can't rotate. The rotation is not allowed because we formed this three-membered ring. Okay, that means the alignment of our substituents that we started with must be maintained at the end of the reaction. Okay, so understanding how the mechanism works allows us to predict that alignment, and that's pretty cool. Okay, what if our reaction had happened the other direction? Okay, well, we're going to get the same kind of concept. Our electrons come out, they go back, they eject, and we would end up with a similar product with our leaving group out there, and we could go through and be showing the same systems, our stars, star, star, and star. So there it is. Cool. We could be like, well, that's fantastic. Was there a difference from which direction this reacted? Well, in this particular case, hopefully you can see that the relationship between these two products is identical, okay, because they have an internal mirror plane. But what happens if we exchange the location of those groups? Now when we go through and look at that product, what happened? Stars, 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 stars. My son is currently trying to beat down the door, so give me a second here. Now, what's the relationship between our structures? Hopefully you can tell that these are now mirror images. Okay, so they're enantiomers. So with our addition reactions, even with the restriction of that ring, we still get the potential for two products. And again, potential for two products. All of that depends on the alignment of the individual substituents that we're starting on our starting material. Okay, so we need to be aware of that when we go through and look at our electrophilic addition reactions. Okay, so let's clean that all up. What could make this slightly more complicated? Because why not? You know, everybody loves having things being more complicated. Is that we could be in a situation where we needed to add a nucleophile. Well, now that nucleophile has to come in and react. Okay, so we're getting a secondary reaction. We said for that secondary reaction to occur that our electrophile had to be positive. Okay, so let's go ahead and say that our electrophile, okay, once it's still connected to the structure, is positive, which means our nucleophile is going to need to come in and react. Now the question becomes, where does the nucleophile come in and attack? I'm going to look at the rightmost drawing. Okay, that nucleophile with electrons needs to somehow share so that the electrophile can become neutral. One option is to have a direct share with the electrophile. What we'll find is that ends up exceeding the octet on the electrophile, and we'd end up forming negative carbons, and that's not a particularly good leaving group. So that's not going to work out so great. So instead, to stabilize that positive electrophile, that electrophile is going to take electrons away from one of the carbons, making them positive. Because they are now positive, our nucleophile can now share electrons. Okay? We are never formally forming a carbocation, and that's one of the things that becomes interesting here. Because we have this cyclic intermediate, the carbocation doesn't come into play, so we don't get any weird interplay, and we'll see that interplay here in a second. The nucleophile has to come in and react to force the ring to open, which brings in another issue. We're talking about the nucleophile coming in simultaneous to that ring breaking. This is an SN2 reaction. We've done an electrophilic addition, and now we're following it with an SN2 reaction. In that SN2, it has to be backside attack, and if we look at the curved arrow that I'm using for the nucleophile, that doesn't really represent a backside attack. A better direction would be a backside attack over here. That's what's then going to cause the ring to open. What does that mean for us? Well, that's going to be the next kind of aspect of our stereochemistry. The wedge and the dash are still cool, however they are, so we aren't really concerned about them right now. Our electrophile bond is now aimed there. If I draw on the nucleophile bond, it's going to have to be over here. Why is this important? Take a look at the relationship between the nucleophile and the electrophile. They are now added on opposite sides of the old pi bond. This is a trans addition. That becomes a problem. Trans applies to pi bonds and rings. We don't have a pi bond, okay? Trans is also an adjective, not a noun. Okay? What we're trying to describe here is the way in which the nucleophile and the electrophile were added to the starting material. So really what we're looking for is an adverb, not an adjective. And so what we need to be using is a slightly different nomenclature system. And that nomenclature system is unfortunately a bit repetitive. This is known as an anti-addition, because the nucleophile and the electrophile were added on opposite sides of our structure. We could also go through in that first step that was our electrophilic addition, we could reference that one as a syn addition, because that syn was the action of how it added. They added on the same side of that pi bond. If you remember earlier, or one of the older videos, I said anti-Markovnikov. Anti was a bad word to use because it could get confused with Newman. We're using anti here in that same kind of not. This is actually referencing the anti-Newman system, where the electrophile and the nucleophile are literally anti to each other in a Newman projection. So the reference to the anti here actually makes a little bit more sense. Okay? So we'd have to be seeing that pop up as a result in our tri-intermediates. So if we can look at our reagents and be like, that's going to form or fit in the category of tri-intermediates, when I draw out products, the two pieces that get added, our electrophile and our nucleophile, they need to be aligned anti to each other. So it can help with some of that kind of memorization process, or you just have to memorize it for each and every single reagent, which is also possible, and people do it all the time. Okay? People also jump off bridges. I don't want you doing that. Okay? That was a bad segue. I apologize. Okay? The same thing is going to happen on the other side. Okay? Again, note the nucleophile and the electrophile on opposite sides. Okay? So the relationship of our products is going to be dependent on that starting symmetry and the identity of the electrophile and the nucleophile. So all of those pieces come together to give us the final arrangement of where all those things align. So let's go ahead and take a look at some quick reagents that potentially fit this category. Okay? If we go through and evaluate this is one that students are like, there's no way in hell that we could have that bromine act as an electrophile. Well, what makes an electrophile? An electrophile needs to be connected to a leaving group. Are you telling me Br- is not a good leaving group? It's a phenomenal leaving group. Okay? And what you might have a hard time seeing is that you see all of the electrons and so immediately assume they're negative. Think back to your oxidation states that you did in 151. The oxidation state for the bromine or the Br, and either Br in Br2 is 0. There is no charge associated with it. It will become charged when an alkene gets close enough to cause that bond to polarize. As soon as it polarizes, our bromide becomes a good leaving group, and the other bromine is our electrophile. So Br is one of the better electrophiles that we get, and it's going to follow this cyclic tri-intermediate structure because that bromine has electrons to act as an intermediate nucleophile or an immediate nucleophile to complete the reaction. Okay? If this reaction was to continue, we would get our cyclic structure here, and you might be like, but that's an awful positive bromine. That's true. So we should break it open. What else do we have floating around? Br-. The Br- can come in. When we go through to look at our product, we should be drawing each of those bromines anti to each other, and we should see that clear alignment. Again, a lot of this depends on the starting symmetry of our molecule. If we're starting with just an alkene, we're not going to see this anti-alignment of those bromines because those aren't chiral atoms and we don't have to worry about it. Okay? So the more substitutions you see on your alkene, the more nervous you should get about trying to ensure that you're showing the proper alignment of those electrophile nucleophiles being added to your alkene. Other structures. The CH2N is another example of this. That becomes a hard one to see until you draw out a Lewis structure. When we draw out the Lewis structure, we've got our hydrogens, we've got our nitrogen, 1, 2, 3, nitrogen, positive, lone pair on the carbon, okay, that, whoops, okay, and the whoops, you might be like, why'd you erase the negative? It has a lone pair. Calculate the formal charge on that carbon. Formal charge on that carbon is 0. That is known as a carbene. So if you hear reference to carbines, they're neat. They're neat because of the hybridization of that system, which I'm kind of nervous that I goofed on, so I'm going to pause and check my electrons. Carbines are just weird, so it's one of the reasons why it freaked me out. But I think, no, I'm still screwing something up. This carbene isn't neutral. There are other carbines that are. So what happens with this one is the electrons can come in. This is a phenomenal leaving group. Okay, we're forming nitrogen gas. Nitrogen gas is incredibly stable. With the extra electrons on that carbene, those can immediately shuttle back, and we form a 3-membered ring with all carbons. This is a fun reagent to mention. It is known as diazomethane. It's fun because it is so explosive and reactive that the people that work with diazomethane are usually missing fingers because their equipment has exploded on them, okay, at least once. The glass, it's so explosive that the glassware, because it's a gas, you got to keep it contained. The joints, if you think back to our labs, because that wasn't only like 3, 4, 5, 6 weeks ago, but if you think back to our labs, when we joined glassware, we had frosted glass. Diazomethane glassware has no frosting because that frosting generates enough friction that can actually cause the diazomethane to explode. So exceptionally reactive species. There are other ways to make carbenes, and we'll see those pop up in one of the examples that I've got later on. The peroxy, if we go through and look at the reactivity of this, the reactivity is interesting because it's in the oxygen-oxygen bond. Okay? If we look, we have a phenomenal leaving group out here because those electrons would be resonance stabilized. That resonance stabilization means that this oxygen starts to become very electrophilic. A pi bond can react by sharing electrons. We kick off the leaving group, the lone pair comes back, and we form what is known as an epoxide. We'll look at the details of those later in the semester. Okay? But we now know how to form them using this reagent. That reagent is very often coupled with an R group out here of a benzene ring with a chlorine located there. This is known as meta-chloroperoxybenzoic acid, or MCPBA. So sometimes you'll see the structure written out, sometimes you'll see it just as the R, sometimes you'll see it as MCPBA, and you, for whatever reason, are expected to just memorize and know that result. I also just happen to remember the last way we could see that. You could see it as an RCO3H. Note the O3 is your tip-off that you're looking at that peroxy. Okay, so there's a variety of ways that we can represent that same chemistry. The last one is mercury, or mercury acetate, as I referenced before. Okay, again, remember the acetates aren't critical. What is critical is that those are leaving groups. If those leave, that mercury has now lost electrons, so it becomes positive. It can act as an electrophile. The part that I find frustrating with the mercuries is we very rarely show that there are d orbital electrons that can complete that 3-membered transition. Okay, so with that, these are our 3-membered, or a pretty sizable representation of our 3-membered transition intermediates, which means I will give you the opportunity to go through and try some practice now with those. Again, hit space, click in your window, pause the video so that we can actually see the products appear after you've already attempted them. So as per usual, we get tons of different things showing up here. So let's start with our simple upper left-hand corner. We're just adding the bromine across the pi bond. We will get the enantiomer. Notice the stereochemistry associated with this. One dashed and one wedged, okay, because they're going in on opposite directions. And the second one down, you'll notice that this statement says no second step yet, and really what this is referencing is a step 1 and a step 2. Some people memorize that second step and associate with it. I have not given that second step yet, so we can't do that. Even then, the product that I drew here is only the reaction with the mercury. Okay? That mercury forms a carbocation, which is an unstable intermediate, very similar to the unstable intermediate formed with our bromine up above. So what happens is we need a nucleophile to come in and do a backside attack. That nucleophile is our water. This becomes questionable because where should that nucleophile attack? We have two potential sites, be it purple or blue. That decision is going to have to do with our leaving group. Okay? The leaving group is that mercury that is currently positive and does not want to be positive, which means it is already trying to leave the structure, which means it's going to try and form the more stable carbocation. The blue pathway is actually the better path when looking at the mercury reagent. The end result for that one ends up putting the mercury out at the tail end and our OH internal. This is going to become a not so interesting one a little bit later on, and we'll discuss the end results of that in a second. Okay, mercury we don't want on our structure, so we'll have to do that second step. That's what is being referenced in that red box. Bottom right-hand corners a little bit more straightforward than the upper right, so let's do the bottom right. We've got a statement there. We aren't showing bond angles appropriately, so it might be nice if we cleaned that up. We have to ensure that we maintain the proper stereochemistry. We started trans, which means we need to end with those methyls on opposite sides. Okay, so that would be a better representation of that, better reflects the bond angles and shows that geometry. If we go through and look at the upper right-hand corner, this is a fun one because all sorts of stuff happens here clearly. Okay, NaOH is the most reactive thing. The pi bond is a nucleophile, so NaOH cannot be reacting with the pi bond. Instead, what it's going to do is react with the chloroform. It will deprotonate the carbon, making it a negative charge, a carbanion. Why would it deprotonate? Is that hydrogen acidic? Based off of an inductive effect of there being 3 chlorines, yep, it's pretty acidic. What can then happen is the chlorine can leave. When it leaves, what we now have is what is known as the carbene. Okay? That carbon has a 0 formal charge. It has both an empty p orbital and lone pair electrons. That is now our active electrophile nucleophile that reacts with our alkene, and we form a 3-membered ring. Note the stereochemistry, we're showing it as wedged. That's going to force that other methyl to be dashed. I did also say plus enantiomer. That's wrong. That is wrong because this other position is not doing any chemistry, which means it stays wedged through this entire process, which means the actual product is not an enantiomer, but is rather a diastereomer of this ugly, ugly thing, virtually impossible to read and see in there. But we would end up with both of those products. So lots of stuff going through on that. It's just going to take practice. You've got a lot of reagents. Start looking up those reagents and start memorizing it, okay, and trying to process those. To give you an idea, I'm going to pause real quickly and go flying backwards towards the beginning of our slides. If we go through and evaluate what we've gotten rid of, we've gotten rid of those 3, that little wedge. What we just addressed was our mercury reagent, okay, which is now showing where those OHs go. If you remembered where the oxygen attacked, it went to the more substituted position. So we've got our oxygens in there. Okay, so those are now addressed. We've also addressed this Br2. Notice the trans alignment of those because they went through an anti-addition. And believe it or not, we have officially now addressed these two. You'll notice that the peroxy was not on this slide because it's on the next one, and the diazomethane did not show up, or the carbene did not show up in the summary slides here. Might give you a tip off that those tend to be kind of one-off reactions. If you're really trying to 100% the class, then you should dig into those reactions. If you aren't trying to 100% and you just want a low A, high B, then you don't need to really push too deep into those. That's probably going to be one question that you weren't going to get right anyway because of how little practice you're going to end up having with it. Okay, so with that, I'm going to go ahead and pause again so we can do a bunch of slide jumping. And there, we've got the end of our Cyclotri, sort of. I do want to address what's going on with the mercury, and we'll move into the next thing. So we've added that mercury to our structure. Mercury's not a nice thing to have connected to our organic structure, so we're going to need to cleave that off somehow. You are not strictly required to know the mechanism for this next part, but what we need is something to eject that mercury, which means we need to have something come in here that is negatively charged. If we looked or remembered the summary that we just were at, you may notice that when we looked at the mercury reagent, what it added was OH and H across the pi bond, which means that mercury somehow needs to get replaced with an H minus. H minus is not a good nucleophile, so it needs some secondary stabilization. That secondary stabilization is going to come in the form of boron, which we will talk about its chemistry a little bit later, but it's going to come in the form of BH4. BH4 will very effectively have the electrons of our hydride come out and directly eject the mercury. The mercury can coordinate with the boron in a pseudo four-membered ring, which we haven't seen yet, but we'll see in just a second. Okay. Why would the hydrogen take the electrons from the boron? Two reasons. One, hydrogen is more electronegative than boron. Not by much, but it is. Okay. The other reason, boron has exceeded its octet, its happy state. If you remember, boron's happy with just 6 electrons around it. It has an empty p orbital. What could we place in that empty p orbital? How about lone pair electrons from hydride? And that's where those electrons are coming from. I know that was a bit of a whirlwind, but that's ultimately what's going on. That has to happen as a second step, because first the mercury needs to be given a chance to do its magic or do its reaction with our pi bond. So we'll see that one split across 2 steps. Oh, I'm going to regret it, but we're going to power through. The last one I want to do before we really break out and stop this video would be tiny leaving groups, or our tetra intermediates. Those leaving groups are now so small that they can't leave on their own, which means they're going to have to react immediately. The big example for this one is BH3. Why is this special? Well, as we just elucidated with our Lewis structure for BH3, it is happy with just 3 groups of electrons around it, which means it has an empty p orbital. Why is this cool? What are we about to react it with? Well, a pi bond with p orbitals. So what can happen is our electrons from that pi bond come out, share with the boron. That would then force out hydride. Hydride is so incredibly unstable that instead of ejecting as a leaving group to float off into solution, there go my hangers, they immediately come back down and react. So what ends up happening is effectively a 4-membered transition state, where we've got our carbons in there, and we're talking about how the sigma electrons of the BH are interacting with the pi electrons of our carbon. And so where all those electrons decide to shift around and move. The pi moves up to the boron, the sigma moves down to the carbon. The end result, if we now shift that around, is that our boron is no longer connected to the hydrogen. The hydrogen is now connected to our carbon, and our other carbon is connected to the boron. What is the alignment, stereochemical alignment of the boron versus the hydrogen? Well, they've now been added on the same side of the pi bond. Why the same side? How could you get this hydrogen? This was an awesome example to do in class with hands and demos. Too bad I don't have that. How could that hydrogen get from the top of your pi system to now somehow be down below? The only way it could get that backside attack is if the hydride was stable enough to come off as a leaving group. In this case, that leaving group is so small and unstable that it can't make that transition, and it only comes in on the same side. Okay? Done a little bit nicer, we've got our hybridization, we've got our p orbitals, we can see the alignment of how these things shift out, and we end up with a product that now puts, and this is where this one becomes a little bit more interesting, our boron and our hydrogen, and the geometry of our methyls being on the same side, might be helpful if I'd actually called that same side, are maintained. Okay, so this is a bit interesting of a reaction. You might also notice that we have a boron on there, and we don't like boron, so we would need to cleave that off. Just like with the mercury, that requires a secondary reaction. The secondary reaction for our boron is peroxide and hydroxide. Okay, and I believe I've got a slide on that in the next second. So with those 3 or 4 membered reaction, does it need to continue? So these first 2 reagents we already addressed. Yes, they need to continue. They have a second step. The osmium tetroxide, which we haven't talked about yet, but we will, okay, sometimes also needs a reagent to continue. So when we're talking about these secondary reactions, you don't really need to know more than they are being used to cleave off the odd elements from our structures, the boron, the mercury, the osmium, and sometimes other elements in other cases. Okay? In most of those cases, you are not required to know the details of those mechanisms, okay? Which is a bit of a thing to say, but also realize where we are in the semester. We've got like 2 weeks left of class. Okay? You don't want to really know those mechanisms. Okay? What you need to know is that when you see BH3, it needs to be followed by peroxide, and it finishes the reaction for you. When you see mercury, it needs to be followed by our sodium borohydride. When you see osmium tetroxide, sometimes you may see it with HSO3. You might also see it with peroxide. You might also see it with water. We'll talk about that with the OSO4. Okay? So you might be seeing these secondary finishers for a reaction. You are responsible for knowing those. Okay? For the boron one, how do we remove it? Okay, very hand wavy but fast mechanism, which is why I like this one. Okay, a full mechanism will show up on the next slide, I think. Okay, there's our BH2. Remember, it has that empty p orbital. Our electrons from our hydroxide can interact into that p orbital, which then means we would need to eject your carbon electrons. We now eject that across, and we end up doing a very similar reaction as our BH3, except now we're going through that kind of slightly different result. The big deal with this is that when we see this, it's all happening at one instant, which means when we add the OH is being added on the same side as the hydrogen. This chemistry is so freaking important that it gets tested on right and left. So when you're adding H and OH using the boron reagent, they get added on the same side. Okay? With that, I'm going to go ahead and now give you an opportunity to do some practice. Almost. Because what I want to do is first show you the mechanism. So here's all the details of it. If you want the mechanism, you can go ahead and click pause. The big thing to get out of it is that the stereochemistry is retained. You can go through and look at all the borate esters. They're cool, they're neat, they're fun. Ultimately, you just need to know they're on the same side. Okay, back to our examples. So I want you to click pause, go through and draw these out. In lieu of actually explaining these, all I'm going to do is draw the answers and leave it at that. That's a lie, but I'm just going to draw the answers and then we'll talk through some of them here in a second. So there are most of our answers with some stuff to be fixed. If we go through and take a look at the first one, you'll notice that one I took all the way to the OH, and I added some questions. I showed the wedge and the wedges to show that the hydrogen and the OH were added on the same side, and then I said plus an enantiomer question mark, and do I need the wedge and the dash? Is stereochemistry necessary in this one? No. There's an internal line of symmetry behind this, which means no wedges and dashes are necessary, which means while I can form the H and the OH on the same side wedged or same side dashed, they're going to end up being no difference in those products, and I don't have to specify wedges and dashes because there's no chiral atoms. There's really only one product. When we move to the one underneath brings in this layer again of asymmetry behind it. Does that change things? Well, remember our chemistry. Our carbon is partially positive there, partially negative here. When our boron reacted, the boron was the one that accepted electrons, and the hydrogen was the one that donated electrons. We need to assign our charges accordingly. The positive goes to the negative goes to the positive, and we would get the reaction or product as shown. That places the boron on the least substituted position, which would then get substituted out for our OH. Here we would need to specify the enantiomer because we do have stereochemistry because of that dashed CH3 in the back there. Okay, that allows us to differentiate this. This becomes an extra fun one as well because you have to identify that regiochemistry. You do not get the product where the OH and the methyl are connected at the same position. If that was the product you wanted, then what you could have used was H2SO4 and H2O, okay? Or the mercury reagent, interestingly enough. Okay, and that's going to add some layer of questions that I don't know that I have explicitly stated in the videos, but I will add in as potential questions for you guys to watch out for. Okay, so there are two ways to add H and OH across a pi, or three ways, H and OH across a pi bond. H2SO4 and water, the mercury conditions, and this borane reagent. Okay, they all result in slightly different things, which is why you need to nuance the difference between those. So I'll leave it for you to decide, potentially to even add in on this slide as a valid question, so that we can address that and make sure that you're aligned for that when it comes to questions. When we take a look at the upper right-hand corner, this is setting you up for that same situation. The BH2 gets added to the least substituted position due to the difference or the regiochemistry of the negatives and positives, which means our OH goes out to the end. This becomes important too. Do I need the enantiomer? Again, no, because there's no chiral atom. So there's no stereochemistry needed to be specified. In the lower right-hand corner, we added the H and the OH. We did all the steps. Why would I have said this wasn't the final product? You have an enol, and enols tautomerize very swiftly to the keto form. For those of you being like, that's not a ketone, that's an aldehyde, it ultimately doesn't matter. It's tautomerizing to the carbonyl. And carbonyl enol doesn't sound as cool as keto enol. Okay? So with that, I'm going to have to call it quits because this is way longer than I wanted it to be. I do appreciate you getting through to this. This is some challenging stuff. It's going to require some practice dealing with those mechanisms and finding out those pieces. You're trying to look for those patterns to simplify how you approach this as opposed to just a raw memorization of reagents. I don't blame you if you decide to take that path though. And with that, I am done.